Okay, now let's try to understand capillary action to some extent in this video as best we can. As you should be aware of, the blood circulation, unlike the lymphatics, is a continuous loop. It leaves the heart, comes back. Remember, the lymphatics were blinded in. The purpose of the bloodstream is to act as a transportation system, transferring good fresh materials to the tissue cells and picking up the tissue cells' waste. Okay, that's the job. The entrance into and out of the bloodstream for the first substance waste is by simple diffusion. Diffusion occurs best through the barrier that's thin. Thus, that barrier would primarily be where? The capillaries, because the capillaries are thin. You can read through this. Okay? Thus, what will happen is then, if the cells in the toe, so in other words, let me put it to you like this. The other blood vessels are too thick. So the arteries, arterioles, venules, except for the postcapillary venules and veins, are too thick for stuff to come in and out. Only the capillaries. The capillaries are exchange vessels. The capillaries are exchange vessels. Okay? Therefore, if the cells in the toe, for example, need some fresh substances or need to unload waste, the blood going to the toe should not enter a thin wall pipe till it gets to the toe. It has to get to the toe first, otherwise you would release your product. Thus, the blood needs to stay in the thicker wall pipes on the way to the toe, and then at the toe go into the capillary bed at the toe. We have to have capillary beds for all the cells, living cells in the body, because that's where exchange. So you get it there, then let them into this true capillary, and then it can unload. That's the purpose of it. Okay? In our continuous loop, the capillaries act as the exchange vessels. All the other vessels, to and fro, act as conduit vessels, getting the blood to the main area for work. So this would be a capillary bed here. All right. So that's where you're going to. Now that means there are millions and millions, I should say billions of capillary beds. Now I want you to, let's concentrate on this capillary bed here. I want you to envision something with me. Okay. Assume all these open areas here, cells are in. Assume all those open areas there that have cells. Now, let's analogize this, if you would, since we normally would be at Kingwood College. Let's analogize this to Kingwood, Texas. Okay. Let's say that this is Highway 59, now Interstate 69. Let's say this is coming from Cleveland, Texas to Houston. Okay. Let's say this is Kingwood Drive right here. This would be the coming off the freeway before Kingwood Drive. Okay, North Park, I believe. Okay. Now, let's say that up in here is the Kingwood division, subdivisions, all up in here. Now, this is how I want you to look at it. Each of them needs to have some stuff happening. All right, we're doing this millisecond by millisecond. That means millisecond by millisecond. So we're going to see how this is going to work. And you don't want to get up in here unless you're ready to deliver, because it's thin wall. So you have to stay away from a true capillary unless you're ready to let your cargo go. Okay, let's say now something is coming this way. Let's say we're going to start with this, that nothing in this area here needs anything this millisecond. Maybe another area does further down towards Houston. So in this millisecond, nothing is needed. Therefore, what happens? The precapillary sphincters right here tighten down. The precapillary sphincters tighten down. Okay? That's going, okay. Precapillary sphincters tighten down. So nothing happens. Let's say the next millisecond, though, you do need some delivery in this area here. Some delivery just in that area there. So it would come down, the precapillary sphincter would relax a little bit. This precapillary sphincter would relax, so you'd go up in this area to deliver here. These other precapillary sphincters would stay fairly closed. That means I would deliver here and not here. So you have some selectivity even in the capillary bed. Now, let's say this one needs it, and this one doesn't. Then you do it that way. Let's say both do. Then you'd kind of unleash this and get up into here. Okay? Now, let's say this is the end of the road. Let's say this was the last on the line. So let's assume that. That means nobody needs anything up in here, but I need to get the blood back to the heart. So think of it this way. You'd come here, you'd open you up, you'd close all the precapillary sphincters, the blood would come down, hit the freeway, and then go on back. So you see, within the capillary bed, because of these precapillary sphincters and metarteriole stuff, that you can get a lot of action even within one of these billions of capillary beds. Okay, so that's kind of what we're looking at. All right, so we go on. Now, this here is what we call net filtration pressure. Okay, I'm going to copy this here and put it over here. Put that over there. Okay. So now what we're going to look at is this net filtration pressure. All right. Now, the net filtration pressure, when we get into that, get here, it's only involving water coming in and out of the capillaries. Let me say it again. This is only involving. Now, there are other substances that come in and out of capillaries, your nutrients, your gases, and other things. But the net filtration pressure right here is only involving water. This guy named Frank Starling, a guy that I talked to about in the heart, known as Starling's Law of the Heart, which says you can't overdistend the heart, says that you should put as much water out of the capillary as you bring back in. You should put as much water out of the capillary as you bring back in. Now let's think if you didn't. If you put more water out than you brought back in, you'd get edema, because you'd have more out here. Vascular edema, called angioedema. If you pull more back in than you put out, it would get dehydrated. So what has to happen? You need to put as much out as you bring back in. All right. So when we look at this, we're looking at the force out of the capillaries minus the force in. The force out of the capillaries minus the force in. The force out of the capillaries. Now so net filtration pressure equals to, this is by international convention, the amount of fluid out of the capillary minus the amount of fluid coming back in. The amount of fluid out minus the amount of fluid coming back in. That's the net filtration pressure. Now, we will do that at the arterial end of the capillary and the venule end. The arterial end of the capillary and the venule. There should be a greater force out at the arterial end and a greater force in at the venule end. Okay? So the forces out of the capillary would be the hydrostatic pressure of the blood. That's the water pressure, which is essentially really the mean arterial pressure there. Now that's a push-out force. Osmotic pressure is a sucking force. Osmotic pressure is the osmotic pressure in the surrounding fluid sucking it out, which has to do with the solution. Remember, isoosmotic, hypo, and everything. The forces into the capillary is the hydrostatic pressure of the water outside here pushing back in, plus the osmotic pressure of the blood sucking it back in. So those are the forces in. So study this. So we go here and we're looking at the net filtration. So let's do our calculations. Let's do our calculations. All right. So I'm saying at the arterial end, the force out, which would be, let's say, the force of the water out, would be the mean arterial pressure. Now, at the arterial end. Now, the mean arterial pressure at the arterial end, would basically be equated to this. See, here's the arterial end right here. You're coming into it, let's say, with about a 35 or 30. Now, remember, I told you that could change depending on vasodilation or vasoconstriction of the arteriole. So we come back. We say right there, let's say around a 35. Okay? So we're just dealing with that. All right. Now, what's the other force? The force pulling out. The force pulling out. So let's say the force pulling out would be about, let's say, a 1. The osmotic pressure pulling out. So I'll say about a 35, let's say, plus a 1. So about a 36 out. Okay, about a 36 out. So I've calculated net MFP here. Now let's go. Okay, so about a 36 out. That would be the out. Minus what's trying to oppose you here. Minus what's trying to oppose you. So we're trying to get that. What's trying to oppose you. Okay. What's trying to oppose you would be the force of water trying to come back in, which we'll say is 0. You say, why is that? Well, we're going to say 0 right now. The force of water trying to come back in. All right. So right now we have a 35 plus a 1 out. 35 is the water pressure coming out. 1 is the sucking pressure. My opposition pressure would be the pressure of the water trying to come back in. Let's look what I'm saying. The pressure of the water trying to come back in. Okay? And we're saying that's a 0 for right now. Then, what's the pressure trying to come in? Okay? 0 for water, but 26 for osmotic pressure. This 26 is the blood osmotic pressure. This 26 is the blood osmotic pressure. Okay? So we had a 36 minus a 26. A 36 minus a 26, which gave us a 10 out. A 36 minus a 26. I want you to study that. Okay? So that's a 10 on this side, which means more pressure out. We come over here to the venule end. Now, what has happened on the venule end of the capillary? The blood pressure's gone down. Why? Because of resistance in this pipe. Remember, we went along this pipe. So by going along this pipe, we went from a 35 mean arterial pressure. Let's go here. Go back. What's that slide? 71. See, we went from, there's my picture. So see, we went through the pipe by the time, here were the capillaries, by the time here, see, I've dropped some pressure from when I came in to here. Why? Because just the length of the pipe. So I've changed the pressure. Pressure's gone down. So we go back. Now on this end, then, the mean arterial pressure is 17. So what do I have as a force out? I have a 17 out, right? Plus the sucking pressure out, which is a 18. That'll give me 18. That's an 18 force out. All right? Now, what do we have coming back in? Well, we said the water pressure is 0. See, the water pressure is 0, even though there's water out there. We'll look at that. And we have this value here of 36. Okay? So I want you to study that. Now I'm gonna end right here and I'm gonna pick this up again. So we're gonna look at net filtration pressure again. Okay?